The last molecules that I would like to discuss with you is water molecule. For the reason, obvious reason, every day you need it, okay? And sometimes it becomes the bad guy. Water vapor is one of the so-called greenhouse gases. Climate change or things like that, okay? So let's look at it within our viewpoint. So hydrogen, easy, just one S. The electron is with one S, therefore you can imagine I will use a hydrogen 1s, but I have two of them, okay, to form bonds. Oxygen, the electronic configuration is 1s2, 2s2, so field, they are not going to do anything chemically, and then you will have 4 more electrons. According to Hund's rule, one of the p state must be filled, and then there will be one lonely electron. I put it in py, another pz. It doesn't matter which one you call it, okay? Therefore, the situation is that for the two py, pz thing, there's an electron waiting to form bond, and therefore a hydrogen could come in here to form a good sigma bond, and another one form another sigma bond, and so on, okay? If it is the case, the prediction will be 90 degree because you use the px/py. But if you do all this energetic calculation with the Hamiltonian and so on, then this angle is extended further. All chemistry book says to lower the energy, the repulsive Coulomb energy of the electron. And I think that makes sense. So if you think about a optimization problem, then you have to try different angles to look for the lowest energy. So it's just like our separation between two nuclei. In this case, in addition to the separation, you need to try different angles. So you have a high dimensional problem to look for the minimum. I know some of you know how to do molecular dynamics things here, okay? You can try that. But in our discussion of physics, it is more important to realize that this structure has a lot of interesting features. For example, it is hetero nuclei. Therefore, the charge will not be even. That is to say, there's ionic character. So the H side will be slightly positive, oxygen side will be slightly negative. Therefore, it is a good molecule to attract charges of whatever sign. Plus is okay, minus is also okay. And that's why in Hong Kong, sometimes in very dry days, you push the button of the elevator, you get shocked a little bit by the static charges there, okay? But in a humid day, you don't have it because we have water molecules around to help you out. They take out some of these charges, attract some of the charges. And also that makes them very good solvent. It could dissolve salt, for example. So sodium chloride go in, so they form sodium plus chlorine minus, and they can be attracted to different ends of water molecules. Another thing I would like to mention here, we may go into that in again after we talk about vibration and rotation of the nuclear part, the nuclear motion part. But water has some very interesting vibrational modes. So it is a mechanics problem. Once upon a time, I think you have 3 balls, a mass, heavier mass, 2 lighter mass, and then you have 2 springs, things like that, okay? Then you can calculate what are the normal modes. One of the normal modes corresponding to this vibration. So as a function of time goes down, bend down, the the O goes up and then comes down again. So it's like what I try to depict here. Now, the interesting thing is that water molecule, due to slightly negative, slightly positive here, so the net positive center of mass is here. Therefore, there is a electric dipole moment in water molecule. As this vibration goes on, this electric dipole moment is changing. For the reason the distance is longer here, the distance is shorter here, I mean the minus charge and the plus charge. So as the molecule vibrates this way, the electric dipole moment is also changing as the molecule vibrates this way. Okay, now this point will be important. Because of this fact, water vapor absorbed infrared frequency at a very particular frequency of this normal mode frequency. But this frequency happens to be fall into the range that the Earth wants to radiate out. So the water vapor in the atmosphere will absorb this Earth radiating out thermal energy. Of course, after absorbing it, it will re-radiate, but only part of it will be going out. Part of it will be re-radiated onto the Earth again. That is to say, it traps some heat. And that is the reason why now, in addition to reducing CO2, actually water vapor is also another factor for warming, global warming. But as you will see a bit later, having an electric dipole moment alone is not the key point. The key point is this electric dipole moment should be changing as the molecule vibrates. That will allow the transition between vibrational states. These vibrational states are oscillator states. Okay, so keep that in mind. You don't have the full formula yet, but as we are talking about water, why not mention? Water is a fascinating molecule. Think about it. What if water is not transparent? Now, first of all, why water is transparent is an optical property of liquid problem. So think about it, dielectric constant, things like that, okay? But practically, if every day you turn on the tap, some dark thing comes in and then you use it to wash your things, and then you use water every day, every hour maybe, okay? So water is a very mysterious and then beneficial materials, worth a lot of attention. So now with LCAO in mind, the next part is something that the goal of the next part is I try to make some previous concept that you may have heard of less mysterious. The first thing is hybridization. I think you have heard about sp2, sp3, things like that, in graphene, in diamond, in silicon, things like that. I will start with the simplest thing called sp hybridization. It exists because the mathematics idea there is the simplest. And therefore, you can get the big picture first, and then carry this into sp2, sp3, life will be much easier. Okay, so let's move on. So the next big topic is hybridization. And accompanying that is the idea of hybridized orbitals or hybrids. First thing first, no new physics. If you follow what we have been doing, it is just LCAO. But when we discuss LCAO, the previous one, we focus on linear combination of atomic orbitals coming from two different atoms. So I have 1s come from left atom, 1s come from right atom. But as we develop the whole thing, we have been emphasizing that if you include more atomic orbitals from one atom and also from the other, actually the calculation should be more accurate. The matrix is bigger, therefore the eigenvalues should be more accurate. Okay? And it is this idea behind hybridization. So hybridization, let me state it at the outset, it is not something special. It is a consequence of understanding an LCAO treatment. Okay, so let's start. Hybridization refers to the following situation. When you include some s atomic orbitals and some p atomic orbitals from the same atom. Now that's the important point, same atom. And then when you do LCAO with some other atoms as well, you do the calculation at the end in order to describe the result. It happens that you will see if you do some linear combination of S and P from the same atom first, the matrix will become cleaner, simpler, okay? And we will call this linear combination of S and P coming from the same atom hybridized orbitals, and this process is called hybridization. So this is all what it is about, nothing fancy. So the first example I would like you to focus on, pay attention to, is beryllium dihydride. So this is BeH2. Experimental fact, it exists. So it is there for us to understand. Experimental fact, it is linear. So 3 atoms in the ground state mode is not vibrating. Well, it could bend a little bit in vibration, but before it does all this complicated thing, basically it's a linear thing, right? We call it a linear molecule. The beryllium is in the middle and H on each side. So these are experimental facts. Now we want to use our quantum mechanics to understand it. The outcome will be, we will understand, I hope, sp hybridization. It's the mixing of one s and one p atomic state of the same atom, namely beryllium here in our example. Okay, so let's see. Now, first of all, from atomic physics, beryllium looks like something that is inert, but it is not, well, because it exists. Okay, it's inert because we thought 4 electrons, 1s2, 2s2, all filled, no fun. It doesn't care about anything. But if you look at the atomic states, then there are some nearby p states around. So in the ground state, they are empty. However, this differs not much by energy. So all the chemistry book says, in order to prepare for the better future, 1 electron is getting up into a p state. Okay, so well, take that story for the moment. You will see actually what happens. So it's like that to get ready for chemistry. So the situation is that we have one electron in 2s, one electron in 2pz. Make sure you understand. Both of them referring to beryllium, same atom. Okay, so we are ready to do LCAO. How many AOs from beryllium? Of course, use this too. That it will be the simplest thing, right? So we are thinking about hydrogen maybe having one electron pairing with one electron here and another hydrogen pairing with the other electron, and therefore there are two sigma bonds happy. It gains some energy, lower energy, this thing exists. Okay, so that is the idea. So beryllium, there will be two AOs. How about hydrogen? I call one on the left 1s. There's another H on the right. I will call it right 1s. Okay, so therefore the linear combination will be of 4 terms. We will get a 4x4 matrix problems. Okay, so let us sketch it. I'm not going to do anything exact here, but if you follow this, you are in good shape. You have some higher level quantum mechanical understanding. Okay, higher than you can do integrals. Therefore, in our LCAO, we have a basis of 4 AOs. We have a hydrogen from the left, 1s. Hydrogen on the right, this is 1s state. Beryllium, we have a 2s and a 2pz. We call the special direction z. It doesn't matter, you can call it x and rewrite it, okay? Therefore, the 4x4 matrix will be set up using these 4 bases on the rows and the column, okay? Therefore, we will have 16 matrix elements. And for the moment, I would like to focus on this 4 elements. Okay, that will be a 2x2 part, entirely have something to do with beryllium 2s and 2pz. So far, do you follow? Any question? Because it is a deep conceptual discussion here. Can you grab what is going on? 明唔明啊？知唔知佛做緊乜先？你知不知道發生什麼事 ？Okay. Any questions? Okay. Now, if not, then let's look into this 2x2 thing. All right. This little part shaded. So this is the part I'm now looking into. It is beryllium 2s, beryllium 2pz. Again, I would like you to remember, they come from one atom, beryllium. So in a pictorial way, I try to draw. Now, this is the nucleus of beryllium. There's only one beryllium atom, but there are 2 orbitals preparing for bonding. Okay, so the S is like a sphere, so I draw it here. The P is like a number 8, a dumbbell, so I draw that with the same center for the reason there's only one nucleus of beryllium. Okay, now I want to change bases in a mathematical sense, or I would like to do some linear combination of 2s and 2p of the beryllium AOs from the same atom. That the later statement is physics. The first statement, the former statement, is mathematics. I want to change bases. What do I want to do? I don't quite like these 2 bases. I want to add them up well, actually there's some square root, maybe there's some 1 over square root 2 outside bracket, okay? That is normalization. I don't care about it here. We are just thinking about the physics. So I can form a linear combination with a plus and a minus. So 2 things goes in, 2 things comes out. No more, no less. This is changing basis, right? Now let's look at the physics. What are we doing practically? So the S y00 has the same sign on the sphere. You draw a sphere, plus is the plus thing. Everywhere has the same sign for the wave function. So if you add them together, there is a region that is plus add into the plus. So this side will have bigger wave function. The other side, you have plus from S, but you have minus loop, this part, okay, come from the P. Therefore, the net will be smaller, okay? So how to draw that? In a very extreme case, it is something like this. Okay, you see a big lobe that looks like an S. Now, this thing looks like the S, the circle, the sphere, okay? And then you have in here something belonging to the P, going out, all right? So this is the plus combination. Now you see what happened. This combination becomes directional. This is pointing to the right. Similarly, if you subtract the 2, what does it mean? Minus PZ. So the minus loop here become a +1. This become a -1. Therefore, it's the same picture, but just pointing to the left. Okay? Now, many books don't draw them one by one. You put the 2 things together, it becomes something like this. This is 2 pictures drawn together, okay? So it is one thing going that, another thing going that, okay? So by doing 2 linear combinations of S and P belonging to the same atom, I must emphasize one more time, same atom, then the resulting combination becomes directional. One points to the right, one points to the left. Or in a chemist way, it says one is focusing the electron density in the positive Z direction, another focusing the electron density in the negative Z direction. Then the next step will be waiting for the hydrogen 1s to come in, because focused at higher density, they will form a stronger bond. The integral of this hybridized orbital with the 1s will be bigger. Okay, this is the off-diagonal element. The pushing will be lower and higher, but you only use the lower one. That is very strong sigma bond. Okay, same for the other side. Therefore, this beryllium dihydride will earn much energy and it exists. That is the whole story. I haven't used hybridization word yet, but this is the whole story. Okay, so now we already saw the eases of hybridization. By forming this 2 linear combination, we said we introduce a new name. We form 2 hybridized orbitals. They are sp hybridized because I'm using 1s and 1p. They are beryllium business, having nothing to do with the hydrogen yet, okay? So if you are still not getting the basic idea, maybe a 1D finite well is easier. So 1D finite well, just one well, so it's one atom. This is the ground state. It looks like an S, right? Same sign everywhere. So the first excited state, change sign plus to minus, is look like a P. So now, if you add them together, positive add to positive is more positive, right? Okay. And this positive add to the negative, it becomes something weaker on this side, and there is a negative part. You do the square probability density, it's look like something like that, okay? Now stretch your mind, use a barbecue fork, and then rotate it, it becomes something like that, quite look like the hybridized orbital. Similarly, you subtract side 2 from side 1, you get the opposite side, okay? So these are the hybridized sp orbitals. So now you may ask, mathematically, no one can challenge what you just did. I'm changing the bases. I have 4 bases. I don't care about the H1s. I just changed the beryllium. I formed the linear combination first, okay? That is legal. No one can say you are wrong, but whether it's useful or not is another business. The answer in quantum mechanics is, it is useful. And it's a good description of nature in forming molecules. So it is one of the unreasonable effectiveness of mathematics in physics again. That is a phrase that I cite from Eugene Wigner, the famous theoretical physicist, who did a lot of group theory in quantum mechanics. Okay, so what for? I think it's now very obvious. Now, one of the hybridized, sp hybridized orbital points to the right, it is focusing the electron density on one direction, and now it's perfect. If I have a hydrogen 1s, this is a plus sign, this is a plus sign, they add together will form a very good bonding state. The integral of this thing with the Hamiltonian in the middle and the 1s from hydrogen on the right, do this integration, that will be a bigger number. This bigger number will appear on the off-diagonal term. They will push lower the MO in energy, okay? So similarly, the same story on the left-hand side, therefore, they will form good sigma bond with the hybridized orbital, and therefore you have a linear molecule and energy is actually lowered. So this is physically speaking. Mathematically speaking, we can write schematically a little bit more. So we start off with this 4x4. We play with this 2x2 block, changing bases here. First, do the combination. So after that, we can rewrite the 4x4, but now in this new basis. Okay, and here's the punchline. I haven't shown you all the numbers because it's quite difficult to calculate all the things. But here is the key idea, why we want to describe it this way. Now, once you prepared this sp hybridized orbital, I call it number 1, pointing to the right, it will couple or it will form a very strong bond with the hydrogen on the right-hand side. So this 2x2 block will be dominating. That is to say, this thing is big, this one is big. And what's more, once you do these changes in bases, you diagonalize this 2x2 part, okay? And then all this thing happens to be very small. Simply put, in doing the linear combination before doing the full 4x4, you block diagonalize the 4x4 matrix at least approximately. Therefore, the bonding story is very clean now. We can think about one hybridized mode pointing to the right is now forming a bond with the right-hand side hydrogen. Another one, number 2, form a bond with the left-hand side hydrogen. And this doesn't matter. They are tiny, tiny. Just pretend them to be 0. Okay? So this block is this quantum mechanics story. This block is this quantum mechanics story. The whole story becomes this story. And then we understand beryllium H2. Okay? BeH2. Okay? So we can separate the bonding into 2 stories now. 2x2, this is now not too small because of focusing electron density. The pushing is stronger, therefore gain more energy. You have 2 electrons forming a bond here. You have another 2 electrons forming the bond there. So this is this bond, this is that bond. The whole thing is linear. Okay. So at this point, any questions? Oh, actually, my physical point is very simple. No new physics. It is LCAO. Any questions? Sanda? So a question comes in. So basically, we choose a better set of orbitals so that overlap. Yes, so that at the end, the bonding will be stronger. Yes, right. Another way to think about it is to think about it, don't think about it at all. Do the 4x4 exactly, diagonalize it numerically, and then look at the resulting basis. Okay? But that will be very numerical. You have no physics to guide you through in other cases. Okay? Do you get that? Okay, any further questions? I just want to demystify something that you may have learned in chemistry. Okay, so let's go on. The next few pages is slightly deeper, but again, the main theme remains no new physics. Okay, so I want to write some 2 electron wave functions out. Again, I will only focus on the beryllium because we start off here and then we do linear combination to form the SP left, number 1 and number 2. I would like to write down the 2 electron wave function in these 2 seemingly different cases. Let's start. So if I have 2 electrons, one in 2s, one in 2p, but I don't know which one is which, what can I do? easy. Selected determinant 2 by 2, right? So one is S, one is P. I have 2 electrons. I do it this way. I call it capital psi, PSI. This is psi 1, 2. Okay, so this is legal. Selected determinant. Now we introduce hybridized SP hybridized number 1 and number 2. So I call it A and B for simplicity. This is actually number 1. This is number 2. Okay, doesn't matter. I call it A, B. Symbols is easier. But then I also have 2 electrons. I have to put one in phi A, another in phi B, so as to spread out the electron, preparing for the strong bonds. But I don't know which one is in which. So what can I do? Write another selected determinant, but now using the linear combined sp hybridized orbitals A and B. I call it phi 1, 2. It is a different thing, okay? Phi, and this is a psi 1, 2. This is in terms of the original atomic thing. This is in terms of the linear combined atomic, so-called hybridized orbitals. Next, are they different? The answer is that no, they are not different. Okay, now let me show you. So I start with the hybridized one, selected determinant, write them out. Then each one is a linear combination. So I just write down all the 4 linear combinations. Nothing fancy. Then there are many terms. I write down all the terms for you, multiply them out. Then you will see there are some cancellations, and then there are terms that are exactly the same and then add up. So you just add them up, okay? At the end, you get that. And that is just the selected determinant. There's such thing. Same thing, nothing fancy. Okay, so here, this 2 pages, more formula. I just want to tell you that after you write down the 4 by 4, whatever you do is mathematically legal. The hybridized thing is nothing mysterious nor fancy. Okay, just the same description, but changing bases to prepare for better bonding picture. We want to get a good physical picture so that we can apply it to other situations. That's the whole point. Okay, so now, next, these 2 pages will be very important because once you get that, SP2, SP3 will follow very naturally. Here, I would like to introduce the systematic way to construct SP hybridized orbitals. Later on, you will use this way to construct SP2 hybridized orbital as well as SP3 hybridized orbitals. By systematic, I mean mathematically systematic. Okay, so let's see. I would like to follow this part, finish this part before we end today. Okay, so now we have S and P orbital from beryllium atom. Since they belong to the same atom, we call atomic orbitals are normalized. So SS is 1. The inner product PP is 1. They are also orthogonal. The reason, same atom. Okay. Now, first argument in constructing hybridized orbitals systematically. The S state is spherical in shape. Therefore, in forming the directional thing, the S state will not bias one of them. You are going to form two. So the S will not say, I will put more of my share to the left-hand side and fewer, less on the right-hand side, or the other way around, because it has no direction itself. What does it mean? It means the following. When I try to form the two hybridized one I call A and B, I want to write down a linear combination, but immediately, due to this equal sharing will not bias anyone, I know the coefficient is 1 over square root 2. The 2 here because I'm forming two hybridized orbitals. Therefore, sp2, you know that will be 1 over square root 3. You are going to form 3 out of 1s and 2p, okay? It means the following, right? This square half is the probability of finding the electron in the S in this combination. So this half means it's not going to bias A or B. Get that? So therefore, what is left is to find this coefficient and that coefficient, then we are done. First, we can use this itself is normalized. We want the hybridized orbital to be normalized to look for CA. Normalized. Okay, what does it mean? Do this. Okay, write it out. There's a S times S term, square root 2, 1 over square root 2 will give you that. This is the unknown. There's a cross term. Because of this, it is 0. So therefore, you can solve for this thing square, take the square root, it is 1 over square root 2. All right? Therefore, you know one of the sp hybridized orbital is this one. Okay? Now, secondly, systematic approach. How to get that? After you get the phi A, then you require sp hybridized orbitals are mathematically speaking orthogonal to each other. The inner product or the integration between them is 0. So we require them to be orthogonal to each other. It's about the inner product, all right? So therefore, we require this to be 0. We solve for the first one. There's an unknown for the second one. Multiply everything out. You have an unknown orthogonal. Therefore, you solved it for this one. Therefore, you have the second sp hybridized one. Okay? So let me summarize. Whatever you do, next time we will do sp2, sp3. We can follow this systematic construction, how to form the best linear combination. Now, in this way, you may think, I can do whatever in higher dimension as well, if you have that world exists, okay? And it's true. So now, with this systematic way, we have this two hybridized sp orbitals. But in spatial direction, be very careful. They are mathematically orthogonal, the inner product, the integral. But in spatial sense, they are 180 degrees apart. How to look at it? Here is the lazy guy way. S, no direction. You have a plus P. It points to one direction. You call that Z. So it points at this side. This one, no direction. minus P point to the minus Z direction. And therefore, in the spatial viewpoint, these two vectors actually dot into a -1. They're 180 degrees apart. And this directionality happens to be very important. Next time, but a long time away from now because you have so-called reading week, okay? I hope that you really read. And then this directionality of the hybridized orbitals is important because although it's local, if you use sp3 hybridization, at the end, you can propagate out into something that worth a lot of money. This is silicon structure. This is sp3 hybridization result. Okay, although the spread out is local, the angle, the directionality is local, it will spread into global structure like this one called FCC, phase center qubit. Okay, so I will end here today. Next time we will do graphene and things like that. Okay, and then we will do diamond structure, and then we will talk about delocalization of electron to lower the energy. That is what happened in metals. So, so long for now. Enjoy your reading week. And I have 23 students at the end of this class. Bye-bye. So I will stay to answer your questions.